Hey everyone, welcome into this video on trig substitutions. In this lecture video, I'm going to just do a bunch of examples for us so we can see how this works. So let's start off. Example number 1. I want to integrate the function dx over, so this is really like 1 over the square root of x squared plus 2x plus 5. So the first thing we need to do is try to get this into a form that fits our trig substitution pattern. So let's remember that if we have a trig substitution, so I'm going to just kind of recreate our table up here, right? So if we have an integrand that looks like a squared minus x squared, then we're going to let our our x equal a sine of theta. And there's a lot of criteria for what the domain of the theta is here, but we talked about that in the last video, so I'm not going to go back into that. If it's x squared minus a squared, then our x is going to be a secant theta. And if it's the square root of a squared plus x squared, then x is going to be equal to a times tangent of theta. Now, this doesn't look like any of those, right? So the first thing that we need to do is complete the square on this internal part. If we complete the square on this, then we can make it look like one of these, right? So just off to the side here, I'm going to take x squared plus 2x and then leave some room and plus 5. And at this point we want to complete the square, so we need to add 1 here. That'll be a perfect square, but we need to then take away a 1 out here to balance it out. And so this then looks like what? X plus 1 quantity squared plus 4, but 4 is 2 squared. All right, and so what we can do then is we can make like a u sub, and we can call this our u, or our x, and this, obviously our a, is going to be 2, right? So I'm going to rewrite this a couple different ways. So our integral right now is equal to dx over square root of x plus 1 squared plus 2 squared. I said a couple different ways. I'm not actually. Let's just go with it from here, right? So this term that's inside the square that has the x, or x plus 1, whatever's in there, has to be set equal to, we have a plus sign, so that's going to be tangent, but it's a times tangent, so it's going to be 2 times tangent theta, right? So 2 tangent theta, and then that means that our x is equal to -1 plus 2 tangent theta, and our dx is of course equal to 2 secant squared theta d theta. And by the way, what's squared down here, the whole reason for doing this is to get rid of that square root, right? So the square rooted part, the x plus 1 squared plus 2 squared, that's going to become 2 times secant theta. All right, and you can check that. So this will be tangent squared, so 2 squared tangent squared, 4 tangent squared plus 4. That's just 2 comes out from the 4, and you're left with a secant theta. So this integral now becomes, after doing this substitution, the denominator is 2 secant theta, the numerator is 2 secant squared theta. So we have 2 secant squared theta d theta goes in for the dx, and in the denominator that's just 2 secant theta. And of course now we have the 2's cancel. Secant's always positive in the domain that we've chosen. And so we have now, this should be the integral of secant theta d theta, which is of course the natural log of secant theta plus tangent theta plus c. But now we need to get everything back in, right? So tangent theta is going to be, we need to go back here and rearrange, right? So I'm going to draw a vertical line here just to separate my answer from some more work that I have to do. So we need to take this substitution and come back over, right? So I'm going to write this slightly differently, right? Tangent theta is going to be equal to x plus 1 all divided by 2. All right, that's just solving this for tangent theta. Same thing here, right? Our secant theta, that shows up in our answer as well. Secant theta is this square root, but this square root is just another way to write the original square root, right? So it's that square root, x squared plus 2x plus 5, again, all divided by 2. And those have to go into our function, right? So now we end up with the natural log of x plus 1 over 2 plus the square root x squared plus 2x plus 5 all over 2 plus c. All right, and so at this point you could combine these fractions. So I'm going to do one more step, and I'm going to be a little crazy about it because you can combine these fractions and then apply a log rule, right? So when you apply the log rule, it's the log of the numerator minus the log of the denominator, but then the denominator is going to be just log of 2. So that can get wrapped up with our plus c, and we can write this answer as natural log of x plus 1 plus the square root, x squared plus 2x plus 5, plus a constant. This constant is not the same as this one. All right, but that's okay, because this one includes a minus log of, includes a minus log of 2 from this one. All right, so there's one example. Let's do a couple more. So the next one, I'll call this one number 2. This one I want to do the integral of x times square root 1 minus x to the 4th dx. Again, this is not exactly in the form of one of the ones from our table, so we have to do a little bit of work before we even start, right? So this one we noticed that we could write this as the integral of x times the square root of 1 minus x squared squared. That's what x to the 4th means. And then we can start this whole process by making a u sub, right? So we can let u equal x squared, and then our du is going to be 2x dx. So let me write this out. So we'll need to do a little maneuvering like this, right? Hopefully we're used to this by now. This should be pretty standard. So our first step, though, is let u equal x squared. Du has to then be 2x dx. And we've got it, right? So this integral now becomes 1/2 the integral square root 1 minus u squared du. And we can try to do this one by a trig sub. So we'll do yet another sub, right? And we're going to have to eventually get all the way back to our x's, right, at the very end. So this time we're going to let u equal, this is 1 minus u squared. So we're going to let u equal sine of theta. And then du is going to be cosine of theta, d theta, of course. And now at this point, what do? Well, we have to remember that the reason for making this substitution is that 1 minus u squared square root is going to be cosine theta. Okay, so it's cosine squared, square root. In the domain of theta that we've chosen, cosine is always positive, so that's just a cosine theta. This whole thing is then the integral, 1/2 the integral of, we make these substitutions. So it's cosine and then another cosine from the du. So this is cosine squared theta, d theta. And we know that to compute the integral of cosine squared, we have to use a power reducing formula. So we get another 1/2 integral 1 plus cosine of 2 theta, d theta. And at this point, we can finally write down the antiderivative. So this is 1/4 theta, right, plus another half. This one's integral of cosine's positive sign, so this will be sine of 2 theta plus c. But now we need to get all this stuff back in terms of u and then in terms of x, right? So we have to get rid of the trig functions first. So the first thing that we notice is this theta, based on this definition right here, right? If u is equal to sine of theta, then theta must be equal to the arcsine of u. This is arcsine. So that's going to go in for that. And then this one, we've got our cosine and our sine. But what about sine of 2 theta? Well, now we need to use another trig identity. So sine of 2 theta is equal to 2 sine of theta cosine of theta, the product, right? So that's a double angle formula. And when we plug this in, that 2 and that 1/2 are going to cancel. So we have now 1/4 of arcsine of u. We're not going to be done even after we do this because we have to get x back in there, right? Plus, this is going to end up being sine of theta times cosine of theta. Well, sine of theta is u, cosine of theta is this, right? So that's going to be u times the square root of 1 minus u squared plus c. And then again, very last step, get this x squared back in there. So we now learn that the antiderivative of x times the square root of 1 minus x to the 4th dx is 1/4 arcsine of x squared plus x squared times the square root of 1 minus x to the 4th plus c. So there we go. Another integral done by trig substitution. All right, I have 3 more on my list here, so we might as well do them. The next one is the integral of x squared over square root of 9 minus 25 x squared dx. And we want to try to do this one, obviously by trig sub. So once again, So this time we have a slightly different situation. So the denominator here, that's the thing that we need to worry about, right? So I'm going to just pull this out and look at this. This is 9 minus 25 x squared. And so this obviously can be written, these are both perfect squares, so it can be written as 3 squared minus 5x squared. And so when we do this, we have to be pretty careful, but what we can do is we can set the 5x, that can be our u, very similar to what we did here, right, with our u, except we can try to do this all in one fell swoop. So we can set 5x equal to 3 sine of theta. This is going to be a sine because it's a minus u squared, a squared minus u squared. All right, so I'm just going to write this down. You can pause the video and think about it. Pause and ponder, as they say. You can think about this if you need to just to make sure I'm doing it right. But I want to put 5x equal to 3 times sine of theta. The reasoning is then obviously that this term right here, 3, so let me write it in the terms that it was given, right? So the 9 minus 25x squared, this will end up being 3 times cosine of theta. So that'll be nice. And then this one, though, what do we get? We get 5 dx, when we take the derivative, don't forget about that 5, right, is going to be equal to 3 cosine theta d theta. All right, and so dx is going to have to be 3/5 cosine of theta d theta. We also need, in this one, an x squared term, right? So this x squared term we have to deal with. So we're going to have to rearrange this a little bit further and write this as follows. So our x is going to be equal to 3/5 sine of theta. That means then that x squared is equal to 9/25 sine squared theta. And so these are the substitutions that we will make. So our integral now of x squared over the square root 9 minus 25x squared dx, this one becomes 9/20, so the integral of 9 over 25 sine squared theta over 3 cosine theta times 3/5 cosine theta d theta. And a lot of this stuff is going to cancel. So let's see what does cancel, right? The 3 and this 3 cancel. This 5 is going to get grouped with the 25, but the cosine thetas also cancel, right? From the integrand down below and the dx here. And so this integral now reduces significantly to become 9 over 125 integral of sine squared theta d theta. And we can compute this by, once again, power reducing or double angle formula, right? So this is going to become 9 over 250, you get a 1/2 power, integral of 1 minus cosine of 2 theta. And this then just gets worked out. So 9 over 250 of 1 minus 1/2 sine of 2 theta. And we just did one very similar to this, right? So we know what has to happen with this sine of 2 theta. This all becomes then 9 over 250 times 1 minus sine of theta cosine of theta, just by their previous work, right? And then we have to plug in, I didn't integrate the 1. That's got to be a theta. It's got to be, right? So there's a theta minus that. So now we go back up and we have to, again, solve for theta. We've got our cosine and our sine, do we? We can have them. We're almost there, right? So we've got our sine for sure. Not really. We need to solve for that a little bit too. So let's just do them all, right? So from this one, we can write what? So our sine of theta is going to be equal to 5/3 x, and our cosine of theta, solve for this one, is going to be equal to the square root 9 minus 25 x squared all over 3. All right, so there's that. That's going to be a product. And then our theta itself has got to be what? Well, theta, we can do that from here. Not really. From here, right? It's going to be the arcsine of 5/3 x. So the arcsine of 5x over 3. All right, now we just put this all back in here, and we get 9 over 250 times, this is going to be arcsine of 5x over 3, minus the product of these two, so this is going to end up being 5 square roots of 9 minus 25x squared all over 9 times x, though. I need to squeeze an x in there. So this should be an x, 5x. All plus c. And then we can distribute this out, and we can write, finally, the integral of x squared over the square root 9 minus 25 x squared dx. This is going to be 9 over 250 times the arc sine of 5x over 3 minus, these 9's cancel, this 5 cancels one of these, right? And so this will be x times the square root of 9 minus 25x squared over, again, 9's cancel, 5 cancels here and makes this a 50, and then plus c. And so there is yet another integral done by trig sub. Notice that that one we did our trig subs slightly differently than the previous one. Either way is fine as long as you get to the right answer, right? So, and then the first one we just had to complete the square. So like I said, I have 2 more. Let's do them. So this next one's a definite integral. This is the integral from 0 to pi over 2 of the function cosine t over the square root of 1 plus sine squared t dt. This is 1 plus sine squared. If it was 1 minus sine squared, we could do some canceling right away, right? But we can't. So our first idea is to do a u sub, right? Try to get our u down here and see what happens up here. So let's see. Let's let our u equal sine of t. And then, of course, for a u sub, you always have to compute your du. Derivative of sine is cosine. So this is derivative, it's cosine t dt. And so this is a nice one-to-one, perfect. We've got everything we need, right, for our substitution here. This just becomes square root 1 plus u squared over du, under du. So it's 1 over this times du. We need to change these boundaries, though, right? So when t is pi over 2, then u of pi over 2 is equal to sine of pi over 2. So that's 1. And when t is 0, then u is equal to sine of 0, which is 0. So this whole integral now becomes integral from 0 to 1 of 1 over square root 1 plus u squared du. All right, and this is actually a stare at it at this point. We could do a trig sub here if we wanted to. This is exactly the example that we did in a previous video, our motivating example, but now it has bounds. So we know that this one is equal to the log of u plus the square root of 1 plus u squared. And we plug in these boundaries, u equal to 0 and 1. This is, remember, the arc-cinch function, arc-cinch of u. So if you need to work this out, pause the video, make your trig sub, work it out. U is going to be tangent theta in this case. You'll have to change your bounds as well. But I'm just going to go with this, all right? So what we end up with then is the log, when we plug in, log of 1 plus the square root of 1 plus 1 squared minus the log of 0 plus square root of 1. So this is the log of 1 plus root 2 minus the log of 1. And log of 1 is 0, right? So this is equal to the log of 1 plus root 2. And that's our answer. We'll leave it in exact form. Always leave these numbers in exact form. The natural log of 1 plus root 2. Okay, so that's that one. And then I have one more. This one's more geometric. I mean, it's not that much different, but this is number 5. So suppose we're given an ellipse, x over a quantity squared plus y over b quantity squared equals 1. So here a, it could be equal to b, but a and b are both positive. They're both positive constants. Then the graph of this is an ellipse. I'm going to draw a perfect ellipse. Wait till you see this. That's a nice ellipse, but look at that. Perfect ellipse. Okay. So that means then in our x direction, this is a, and in our y direction, this is b, right? And there's our ellipse. What I want to know is what's the area of this ellipse? All right, so find the area. By the way, you probably know the answer, but I want to compute this as an integral. So use an integral to compute the area of the ellipse. The way I'm going to do it, because of symmetry, is just find the area in the first quadrant and then multiply by 4. All right, so 1/4 the area is going to be equal to the integral from 0 to a in the x direction of whatever the formula for this function is, right? So that's, we'll call this y. just for now, but this is our y equals f of x in some sense, right? So integral of y of x dx. So that's what we want to compute, but that means we need to solve for y. So we go back to this equation and we rearrange, right? So y over b, quantity squared, is going to be equal to 1 minus x over a, quantity squared. Take the square root, multiply by b, and we get that y is equal to b times this square root of this function. And since I restricted to quadrant 1, then the square root is positive. There's no problems with the square root. The y itself is positive. Okay, so this is the function that we want to integrate. So 1/4 of our area, again, is equal to the integral from 0 to a of this integrand, b times the square root, 1 minus x over b squared dx. This is very similar to what we integrated up here, but let's do it again, just for the practice. All right, so we need to make our substitution. The b can come out, by the way. This b can just come out here. And then we make our substitution. So now we're going to let x over b equal sine of theta, because we have 1 minus u squared, right? So that's sine of theta. And then our dx over b, so 1 over b dx is going to be equal to cosine of theta, d theta. So this then means what? That our dx is actually going to be equal to b cosine of theta, d theta. And our integrand itself, this 1 over x minus, this is supposed to be x over a. Sorry. That's got to be an a. This should have been an a. I made this, I'm sure you guys were yelling at me. I couldn't hear you. So there's an a. This has got to be an a. This whole thing becomes just cosine of theta. That's the idea, right? All right. So let's plug in then. So we have 1/4 of our area equals, the b comes out. We have integral from 0 to a times the integrand becomes what? This is going to be cosine theta, and then the dx is an a cosine theta. So this becomes a cosine squared theta d theta. We got a problem though. I made this mistake, which I always am very careful not to make. These are x values, right? We need to plug in. So before we go any further, let's go back and check that. So when x is equal to a, we need to rearrange this, right? We need to solve for theta. If we want to do this without going back, right? Theta then is going to be equal to the arc sine of x over a. So theta when x is a is equal to the arc sine of a over a. Arc sine of 1. Arc sine of 1 is pi over 2. All right? Theta of 0 is going to be equal to the arc sine of 0 over a. When sine is 0, theta is 0. All right? So the boundaries actually become 0 is fine, but this becomes pi over 2. All right? And then we'll get a number for this. So let's keep computing. Now we're back on track. 1/4 a is now equal to a times b times the integral 0 to pi over 2 of cosine squared theta d theta. We need to use our double angle or angle power reducing formula here. So this then becomes a times b over 2 times integral 0 to pi over 2, 1 plus cosine of 2 theta d theta. Now let's integrate. So ab over 2, this one is going to be theta. This one's going to be 1/2 sine of 2 theta. We've done this a couple times in this video. Plug in our theta values from 0 to pi over 2. So the first part, we have this ab over 2 just hanging out. Then we have pi over 2 minus 0 plus sine from 0. This will end up being 0 to pi for the sine function. Sine is, and it's going to be, well, let's just plug in, see what happens, right? So this is going to be 1/2 sine of pi minus 1/2 sine of 0, but those are both 0. All right, so those are both gone. And then we end up with 1/4 of the area of this ellipse is equal to pi times a times b over 4. So that means that the area of the ellipse is pi times a times b. And that's exactly what it should be if you remember for an ellipse. Ellipses have like a major radius and a minor radius. you multiply those together, multiply by pi, right? And if this ellipse was a circle, what would be true? A would be equal to b, which would be equal to r, the radius, and you'd get pi r squared. So this is the right answer computed by trig integral. Trig substitution, I should say. All right, so I'm going to leave this video here with these examples as 5 examples. So please enjoy.